Imagine taking a brain the size of the internet and teaching it a complex new skill using nothing more than a sticky note.
That is essentially what Microsoft just figured out how to do with large language models. Welcome to our podcast, Artificial Intelligence, Papers and Concepts curated by Dr. Satya Malik.
And before we get into the weeds of today's paper, we should mention that for this deep dive, both myself and my co-host here are AI-generated voices.
We are literally the technology we're talking about today.
Exactly. And the paper we're unpacking is called LoRA, Low-Rank Adaptation of Large Language Models. It's from Microsoft. And, if you're building with LLMs right now, this is probably one of the most important breakthroughs in years.
I really don't think that's an exaggeration. The mission for this deep dive is pretty clear. We want to understand how we went from the old way of fine-tuning, retraining a whole massive model to this new world where we just train a tiny, tiny update.
Right, how to customize something like GPT-3 without, going bankrupt on GPUs.
Precisely. To really get why LoRA is such a big deal, we have to look at the before picture. The status quo in NLP. You start with a pre-trained model. Think of it like a generalist.
Let's read the whole internet.
Yeah, it knows grammar, it knows facts, a little Python, maybe some French cooking.
But it's a jack of all trades, master of none, right? If I want it to, say, summarize legal contracts, the base model is okay, but not great. It makes stuff up.
Right, so you have to fine-tune it. You basically send it to grad school, you show it thousands of examples, and update its weight so it gets really good at that one specific job.
And this is where we hit the law, the scaling issue.
The scaling issue. These models are getting just huge. GPT-3 has 175 billion parameters. And in the old way of doing things, fine-tuning meant updating all 175 billion of them.
Okay, hold on. I want to pause on that number because it's easy to just hear billions and move on. What does that actually look like, hardware-wise?
It looks like a burning pile of money. The paper says to fully fine-tune GPT-3, you need about 1.2 terabytes of VRAM.
1.2 terabytes. For context, a really high-end gaming GPU, like an RTX 4090, has what, 24 gigs?
Exactly. So you'd need a cluster of like 50 or 60 of those cards all working together just to hold the model. And that's for one single fine-tuning job.
And that's the other bottleneck, right? Deployment.
Yeah.
Let's say I'm a SaaS company. I want to offer a custom model for each of my clients.
If you use full fine-tuning, you're creating a brand new 175 billion parameter monster for every single client.
Yeah.
Each one is hundreds of gigabytes. If you have 100 clients, you're trying to store 100 slightly different copies of the internet. It's impossible.
It's like building a whole new library for every person who just wants to read a slightly different book.
That's a great way to put it. And, researchers knew this was a problem. Before LoRA, there were other attempts like adapters and prefix tuning.
Right, adapters. The idea there was you freeze the big model and just wedge in some new small layers. Right?
Yes, exactly. You only train those new little layers.
Yeah.
It solves the storage problem because the new parts are small.
But there's a catch.
There's a catch.
Inference latency.
In plain English, the model gets slower.
A lot slower. The paper shows it can add over 30% more time to generate text. It's because you're adding these extra steps, like little toll booths on a highway. The stopping and starting just kills your speed.
That's a deal breaker for anything real time. So what about the other one? Prefix tuning.
That's where you learn a special prefix, like a set of instructions you stick in front of your prompt to guide the model. But the problem there is it eats up your context window.
Your sequence length.
Right. If the model can only handle 2,000 tokens and your fancy prefix takes up 200 of them, you've just lost 10% of your workspace for the actual user query.
So we were stuck. Option A is crazy expensive. Option B is too slow. Option C makes the model short-sighted.
A series of bad trade-offs.
Yeah.
And that is the perfect setup for why LoRA is such a massive breakthrough. But before we get to the solution, we have a quick message. We do. This podcast is sponsored by BigVision.ai, a consulting and product development company that helps companies of all sizes build computer vision and AI solutions. You can reach them at contact@bigvision.ai.
Okay, so let's solve this. LoRA, low-rank adaptation.
Low-rank adaptation. It sounds heavy on the linear algebra, but let's start conceptually. The big model's weights are frozen, locked. We don't touch them.
Correct. The 175 billion parameters are read-only. What LoRA does is it injects these tiny trainable rank decomposition matrices into the layers.
Okay, let's go back to my sticky note idea. If the model is an encyclopedia, full fine-tuning is rewriting every page.
Right. And adapters would be like gluing extra pages in, making the book thicker.
But LoRA, it's like putting a transparent overlay on top of the page. You write your notes on the overlay, and when you read, you see the original text plus your changes.
That is actually a surprisingly good visualization of the math. Under the hood, a layer is just matrix multiplication. You have an input, and you multiply it by a weight matrix, let's call it W.
And learning is changing W. So new W equals old W plus some change, some delta W.
Exactly. W equals W0 plus delta W. Now, traditionally, that delta W is the same huge size as the original matrix. If W is 12,000 by 12,000, so is delta W.
Which is why it's so big. But the LoRA authors had this hypothesis.
They said, wait a minute, do we really need to change all those numbers to teach it a new trick? The idea is that the change needed for a task has a low intrinsic rank.
Let me try to translate that. So, you're describing a drone flying in a room. You could describe the position of every atom, that's high rank.
Right.
Or you could just describe its direction, a simple vector. That's low rank. The change is simple, even if the object is complex.
That's a brilliant way to put it. The update doesn't need to touch every dimension. So instead of storing that giant delta W matrix, LoRA represents it as the product of two tiny matrices, a tall skinny one, B, and a wide flat one, A.
And you only train B and A.
Exactly. So if the original dimension is 12,000 and you choose a tiny rank, say R equals 8, you're training matrices of size 12,000 by 8 and 8 by 12,000. It's a massive reduction in parameters.
Okay, that makes sense. It's smaller. But how much smaller? Give me the aha stats.
With GPT-3, LoRA reduces the number of trainable parameters by 10,000 times.
10,000 times.
And for storage, a full fine-tuned checkpoint is about 350 gigabytes. With LoRA, it drops to 35 megabytes.
Wait, from 350 gigs to 35 megs?
Yeah.
That's not a hard drive anymore. That's an email attachment.
Exactly. You've moved from hard drive scale to email attachment scale.
Yeah.
For that SaaS company we talked about, you just keep one base model loaded and swap these tiny 35 MB files in and out. It's instant.
Okay, I have to play devil's advocate. There's no free lunch. If you compress something by 10,000 times, you have to be losing quality. Does the sticky note actually work as well as rewriting the book?
That's the part that shocked everyone. The answer is yes. The paper shows LoRA performs on par, or sometimes even better than full fine-tuning.
Better? How can it be better with fewer parameters?
It's likely a form of regularization. Because you can't change everything, you're less likely to overfit. You're also less likely to suffer from catastrophic forgetting, where the model learns the new thing but forgets the old stuff.
Okay, so it performs well. But what about the latency problem we saw with adapters? Aren't we still adding extra math?
But here's the magic trick. During training, yes, it's separate. But when you're ready to deploy, you can merge the weights.
Merge.
You just multiply your B and A matrices together to get that big delta W matrix back.
Yep.
And then you simply add it to the original frozen weights. W new equals W old plus B times A. You bake it in.
You bake it in. So after you merge, it's just a standard model again. No extra layers, no toll booths.
Exactly. Zero added inference latency.
That is just brilliant. You train it efficiently, but you deploy it fast.
That's the key.
I want to go back to that rank idea. You said it was the complexity of the update. For something like GPT-3, how low did they actually go with the rank?
This is the part that's just mind-blowing. Remember, the original dimension is over 12,000. They found that a rank, an R, of just 1 or 2, was often good enough.
Wait, 1?
Yeah.
A rank of 1? You're telling me you can distill the entire concept of write me SQL code into a single vector direction?
In many cases, yeah, or at least to get you most of the way there. It implies these models are massively over-parameterized. The capabilities are already there, floating in the soup. They're just quiet.
So LoRA isn't teaching the model what a database is?
No, it already knows that. LoRA is just pointing a flashlight at that knowledge. It's an amplifier. The paper found it could amplify certain features by up to 20 times. It's just shouting, hey, use this part of your brain.
And they figured out which parts to shout at.
They did. They found adapting both the query and the value attention weights gave the best results.
So what am I looking for, and what information do I pull out are the key knobs to turn?
That's right.
Okay, so let's do a final scorecard. I'm an engineer deciding what to use. LoRA versus full fine-tuning.
LoRA uses 10,000 times fewer parameters, 3 times less GPU memory, and performs just as well. Winner is LoRA, hands down.
LoRA versus adapters.
LoRA has 0 latency penalty. Adapters slow you down. Winner, LoRA.
And LoRA versus prefix tuning.
LoRA doesn't need your context window. Prefix
Yeah.
tuning does. Winner, LoRA.
It seems like there's no contest. This is the tech that democratizes these giant models.
It absolutely is.
Yeah.
A few years ago, fine-tuning GPT-3 was only for, Google or Microsoft. Now, because LoRA drops the VRAM requirement so much, you can fine-tune a powerful model on a single consumer GPU.
On a gaming PC.
A kid in their dorm room can customize a state-of-the-art AI, and they can share it. It's the Napster moment for AI models.
That is a powerful image. And it leaves me with one final kind of provocative question.
I think I know where you're going.
Go for it.
If we can radically change the behavior of a 175 billion parameter model by tweaking just 0.01% of its brain, what are the other 99.99% of the weights actually doing?
Are they just dead weight?
Are they redundant?
Mm.
Or are the tasks we think are so complex, like writing code, actually much simpler, mathematically, than we give them credit for?
That is something to chew on.
Yeah.
Are we building these giant, inefficient brains to do simple things?
I think it's just proof that we're still in the very, very early days of understanding how any of this really works.
On that note, we're going to wrap up this deep dive. Thank you so much for listening.
Thank you. And if you enjoyed this breakdown, please subscribe. We have plenty more deep dives into complex AI papers coming your way.
See you next time.